Look at any stable structure, like a bridge under load or a ladder leaning against a wall. These objects maintain an active state of equilibrium, where every inward force is perfectly canceled by an outward reaction. This balance follows three specific mathematical conditions. For any two-dimensional rigid body to remain at rest, the sum of forces in the x direction must be 0, the sum of forces in the y direction must be 0, and the sum of all moments, the rotational forces, must also equal 0. Proving these three equations equal 0 is the primary task of structural engineering, whether the project is a simple shelf or a massive skyscraper. We analyze these systems using a free body diagram. By isolating the object from its surroundings, we can focus exclusively on the forces acting upon it: applied loads, the self-weight pulling down from the center of gravity, and the reaction forces at the supports. The arrows we draw depend entirely on physical constraints. If a support prevents movement in a specific direction, it generates a reaction force arrow in that exact direction. Take this roller support as an example. It allows the beam to slide horizontally, but prevents it from falling. Because it only restricts vertical movement, we represent it as a single upward reaction arrow. A pin joint is more restrictive, blocking movement in both horizontal and vertical directions, which requires two arrows. A fixed support goes further by preventing rotation entirely, adding a third curved arrow to represent the resisting moment. Correctly translating these physical limits into reaction arrows is a mandatory first step. If the diagram is wrong, the math cannot be right. Consider this baseline problem: a beam with a pin support on the left, a roller on the right, and a downward point load in the center. We translate this into a complete diagram, with two unknowns on the left and one on the right. To solve for three unknowns, we start by taking the sum of moments at the pin joint. Because those left side reaction forces pass directly through our axis of rotation, they create zero moment. This effectively eliminates two variables from our initial calculation. Once you have the right side reaction, you can find the remaining forces by simply summing the horizontal and vertical vectors. This classical method works for any non-concurrent system, but solving multiple algebraic steps can be time-consuming during a test or a rapid design phase. When exactly three concurrent forces act on a single node, like a weight held by tension cables, we can bypass the standard equations for a faster solution. We apply Lami's theorem. This shortcut states that each force is proportional to the sine of the angle between the other two forces. However, there is a critical trap. Lami's theorem fails mathematically unless all three forces point away from the central node. If your diagram has forces pointing inward, use the principle of transmissibility. You can slide these inward vectors along their line of action to the other side of the node so they point outward. Try it yourself. Pause the video here and mentally redraw this system so all three forces point outward. Calculate the new angles between those vectors. By sliding the inward forces through the origin, we create a valid outward-facing diagram. These are the corrected angles you need for your sine calculations. Taking 10 seconds to orient your vectors outward is the prerequisite to using Lami's theorem correctly. This shortcut applies to complex cases like a wedge lifting a heavy block. The rough surfaces generate two reaction components, a perpendicular normal force and a parallel friction force. We combine these into a single resultant vector, creating a manageable three-force concurrent system. Recognizing these physical resultants allows you to solve advanced friction problems with the speed of a simple Lami's theorem calculation. To summarize, remember your support rules: 1 arrow for rollers, 2 for pins, and 3 for fixed supports. And if you use Lami's theorem, verify that every force vector points away from the node. Successful structural analysis depends on the diagram that precedes the math. When you accurately translate physical constraints into vector arrows, solving for equilibrium becomes a simple exercise in balancing equations.